So let's see if everything's working correctly and if my voice is broadcasting correctly. There will be some delay, I guess, but I'll just first check that I will hear my voice in the stream and then I'll begin. Maybe my voice could be a bit higher, but I think that's fine. So I will start now. So I would suggest you guys having the problems and the model solutions open in a window, since I won't be copy pasting them here. I will be just going through the problems, and in particular I will be focusing on like the problem solving aspect, and with certain problems there exist more elegant solutions than have been posted officially, so I will go over those as well. And since I will be going through all the problems, and especially as the first problems are intended for beginners, I will also go through those problems as if every one of you would be a beginner. And with the later problems I won't be focusing too much on the trivial / basic things. But yeah, and I also hope that this stream will be like less than 2 hours, so I shouldn't be spending 10 minutes per each problem. So yeah. Well, the first problem was like, it wasn't that difficult. There were some problems with the wording, like it wasn't immediately clear what was the situation for everyone. But otherwise, the idea is that we have an intersection. So some sort of an intersection here. And then there is some type of crosswalk / zebra crossing, but then we have a jaywalker who is too lazy to go around, so they're just going straight across the street at a certain distance from this intersection, X, but then there is a car, like this, going also at the intersection, but there's a different distance, capital X, and then we are given some information. First of all, it takes time t for the jaywalker to cross the road, and the velocity / speed of this car here is such that it will reach the intersection in this same time t. But at the same time at t equals 0, when all of this is happening, there is a red light at the intersection. So this self-driving car, which doesn't recognize the jaywalker, will start decelerating in such way that it will stop right before the intersection. And based on this, we are supposed to determine whether or not a crash will happen, and we are assuming that this car covers the whole street, basically. And for a beginner, this might seem like that there's not enough information to solve anything, since since we are given numerical values for capital X and small x only. We are not given this time t, so we cannot determine the velocity, nor do we have information to determine the acceleration numerically. But in these types of problems, especially if you're a beginner, and you are not sure whether or not there's enough information, you should just start doing math. Assume that everything is known, and if you are lucky, the things you don't know will cancel away. So we will use this approach now. So let's assume that we know this t. Well, then this speed of the car is very easy to calculate. It is simply x over t. Similarly, the deceleration is very easy to calculate using the kinematic equation v v squared is equal to 2ax, because the car will stop at the intersection. So that way we calculate that a is equal to v squared divided by 2x, which is just x divided by 2t squared, using this relation here. And then to determine the position of the car at the moment t, we can use kinematic equations as well. And why this is useful is that if the car would be, let's say, here when the time t has passed, then there will have been a crash. If it's here, then there will be no crash, because then the J-warp has crossed the road. So we want to determine the position of this car at the moment t to determine whether or not we are looking at a crash or not. So we can determine this once again using some kinematic equations. Let's say that the car will travel some distance L. So then L is simply equal to the initial velocity times the time passing minus 1/2 the acceleration t squared. And now we can just plug in the information we have already found to find that this is x minus 1/2 x divided by 2. So we notice that the t's cancelled out, which is what we wanted, so perfect. And now we are pretty much done with the problem. This is 3/4 x, which is 30 meters, and as this big X was 40 meters, then we are 10 meters away from the intersection, which is larger than 8 meters, which was small x, which means that no crash happens. The car will be like somewhere here at time t, and we wanted and in the case that no crash happened, we wanted to find the distance between J-walker and the car at the moment t, and this is simply this 10 meters minus x, which is 2 meters. All right. Yes, I should also probably put the chat in such a way that I'll see it if there's some relevant questions there. Just wait a moment, because YouTube is sometimes a bit finicky with this. Or it might be just my browser issue. I just want the chat to load. Meanwhile that's happening, actually I can just look at the chat from my laptop. Okay, fine. So then next problem. This next problem was, well, I would say, like, it is an easy problem, but optics, and especially wave optics, isn't like it's not something many beginners know. So even though it's an easy question, it's not really for beginners. So we basically have a tube with an interesting solution where like right and left-handed circularly polarized light behaves differently. They have different refractive indices. And then we want to find that because of this difference, the polarization of the light will start to rotate. And we want to find this rotation, total rotation basically, when the light has passed through this entire tube, which had like length L. Sorry, I need to drink some water. First, so I don't die. Okay, so how do we approach this problem? Well, because the refractive indices are given for circularly polarized light, but the incoming light is only linearly polarized. This immediately tells us that we should somehow represent the linearly polarized light using circularly polarized light. And this leads us to think about superposition. Okay, so how can we represent the linearly polarized light using superposition of left and right circularly polarized light? Well, let's think about it. The electric field of a linearly polarized light will just oscillate, for instance now vertically. I just decided to write it this way. But an oscillation can always be written as a superposition of two vectors which are rotating at different directions. So there will be, at one moment of time, there might be a like these two vectors, which will superpose to create some total electric field. And now these two electric fields which we are superposing are rotating. This is rotating like clockwise and this is rotating counterclockwise. And if you think about it in your head, this will create this sinusoidally oscillating electric field. Great. And now we just want to find what happens when these two rotating electric fields have different refractive indices while they are passing through this tube. And the idea is that this will change, this will affect the phase of these oscillating fields. And what do I mean by phase? Because both of these are basically like any oscillating thing can be typically represented using trigonometric functions. So the electric field will be like proportional to some sort of cosine term, which we typically write something in a form similar to this. Sometimes these might be swapped or whatever. And now we and this is what is called the phase. This tells at which point of this oscillation cycle we are in. And because they have differing refractive indices, this phase will be different. But why? Well, we first notice that this part here will be the same for both of these circularly polarized electric fields or light sources. This is because we are measuring the electric field at the end of this tube here, and when we see that electric field, both of those light waves have had the same amount of time to reach our eyes. And also omega is basically the frequency of the light, and that doesn't change when the light goes inside the tube. So we don't care about this term, we care about this term here. And so what is happening now? So the phase, which is here phi, and basically the reason why the phase will be different for these two circular polarized light, this kx term is different. Of course this x term is the same for both, because both of them have traveled through this entire length of the tube. So we have that the change in phase is the change in kx, and that change must only come from k, since they both travel the same distance L. But what is this k? This k is a so-called wave number, or in high-dimensional cases, you also look at the wave vector. But this is basically one-dimensional, so we can talk about the wave number. And because we want this phase to go through a 2 pi, go through a full oscillation when a wavelength has happened. So if we think about a wavelength, it's the same part of the oscillation when some wavelength has happened. And for this cosine to go through a full oscillation, this means that when x increases by L, this means that this k must be 2 pi divided by L. And now, the key insight here is to realize that the wavelength can be different when you enter a medium. You can see this, for example, from the fundamental relation of waves, where the speed of a wave is determined by its frequency and its wavelength. And because the frequency stays the same, and v for light is simply c divided by n, where n is the refractive index, we can clearly see that L is proportional to 1 over n. So we get that this delta k here is delta 2 pi, the original wavelength divided by n, which is simply 2 pi lambda delta n. So now we have found a phase difference between these two oscillating vectors, basically. And now we just have to do some geometry. So what do we mean by this phase shift geometrically? Well, in the normal case, when they are at the same phase, it means that, let's say, this counterclockwise moving vector, its projection to the other side of this circle gives us the other clockwise moving phase vector. But because there's now some phase difference, one of these will have gone faster, slightly bit faster, so let's put it like this. And geometrically, this angle here will be that delta phi. But now we wanted to find the total rotation of the superposition of these two waves. And we can clearly see that the superposition must always lie along the now I have to think about English, the angular bisector, like something like this. The superposition will lie here, and this will have rotated some with some amount respect to the vertical where it started from, and this is what we want to find. But now using a bit of geometry, because this is the angular bisector, this yellow angle and this yellow angle will be the same, and because of this reflective property, we have that these red angles must also be the same. And we can call this red angle, let's say, phi 1. And the yellow angle we can call, for instance, alpha. And now we can say that alpha on the left hand side is simply phi 1 plus delta theta, but on the right hand side it is phi 1 minus delta theta plus delta phi. And then we just take the difference of these two equations to have that 0 is equal to 2 delta theta minus delta phi, and that gives us that delta theta is delta phi divided by 2, which is simply pi L delta n times L. And we are done. Okay. And then the next problem, I have spent quite a lot of time for these two problems, but let's hope that doesn't continue. Okay, well, now this is this ball drop problem is a really simple basic kinematics problem. I will only show you the physics and I will leave out the math, basically. Because once you have the equations, you can just use a computer algebra system or some sort of calculator Wolfram alpha to solve it to the end, and that is like irrelevant. So we have a pool of liquid with some density rho b and some depth d, and then we have two balls of some density rho b. Oops, this was supposed to be rho p, and this is at some height h. And we know that the radius of these balls is basically negligible, but these balls have some volume, and we can neglect like the splash that happens once this ball hits the water. And we want to find what is the relation between D and H, such that both of these balls will hit the bottom at the same time. Okay, well, it is easy to find the time of this ball here, which is starts at the surface. Well, we just have to find the acceleration inside this liquid, and that acceleration can be calculated from the total force, because acceleration is just the total force divided by mass. And the total force is the gravitational force minus the buoyant force, which we can calculate using the Archimedes principle. Alright, so this is simply 1 minus rho b v divided by m, and this m can be calculated using the density of these balls. So we have simply that rho b v, oh, this should be p, v rho p v. So then we have that g is like rho b. I'm constantly like putting these the wrong way around. Rho pv divided by rho bv, and this is g is equal to rho b minus rho p rho b, and this was defined to be r in the problem statement, so this is simply rg. And now the rest is just kinematics. The balls will accelerate with the acceleration a inside the liquid and with acceleration g when outside of the liquid. So the time which for this ball to reach the bottom can be calculated using the basic kinematic equations, like 1 over at squared is equal to d, and t is then square root of 2d divided by a. And for this second ball we can like calculate the time it takes it to hit the liquid and the time it takes to reach the bottom from there. So the time to reach the liquid is we can use the same equation, basically 1 over g t1 squared is equal to h. So t1 is simply 2h divided by g, and t2 can be calculated in several ways. The most obvious way is to first calculate the speed at which this ball hits the water, and then use this similar type of equation. So the speed at which it hits the water can be calculated easily from the kinematic equation of v squared, the change of v squared, so v is 2gh, and then we can calculate t2 from vt2 plus 1 over a t2 squared is equal to d. There is a slightly easier way and more elegant way in the model solutions, where you calculate using this same type of equation. You calculate the speed at which it hits the bottom, and then t2 is simply v final minus v divided by a. This is slightly better since it minimizes the risk of you using the quadratic equation, the quadratic formula wrong, because sometimes you input the things do some silly mistakes, but that doesn't really matter. And the last part is simply equating that t is equal to t1 plus t2, and then you solve and then you can plug in the d is equal nh, and then you solve for n, and yeah, the rest is just math. Nothing interesting in this problem. Then is the coil fun problem. This is actually quite tricky. I am surprised it was like it's easy. The solution is easy, but the problem is tricky. Let's put it that way. So we have a superconducting coil, and then we have some metallic core, and these both have the same dimensions. And this core starts from and this core has some relative permeability, mu r, let's say. And this core starts from infinity, and due to magnetic forces it starts to go to the superconducting coil, and then we are able to stop the superconductivity of the coil and stop the current at any point we want, and then we just want to find what is the maximum velocity at which we can launch this core through the coil. And here there is a this is not as trivial as the solution makes it seem like. The idea is simple. Well, the idea is simple since if we use energy, there is two sources of energy for this system. It is the kinetic energy of this core plus the potential energy from the magnetic fields. And when we cut the current, we can set UB to disappear from this energy, so we can just get rid of all of the energy related to the magnetic fields, and that will go away, basically. So thus we want to cut the current at the position where the magnetic potential energy is at its lowest, because then the kinetic energy will be its highest. But what will be that point? And that is not a trivial answer. But luckily there is some symmetry we can use. Because first of all, the force on this coil is simply du dx. This is like the definition of potential energy. Now, we want to cut the current when U is at its lowest. This means that du dx is 0. Now there is, by symmetry, there is 3 points for this. When the core is at infinity, which clearly corresponds to the highest magnetic potential energy, and when the core is directly inside the coil. And clearly that minimizes and clearly that is a local minimum of the potential energy, because if I displace this core, I break the symmetry, and the core wants to get back inside the coil. So I want to cut the energy at this position. So, what is the magnetic potential energy at this point? Well, because the core is superconducting, the flux through the coil will always be the same. And this flux is NAB. But clearly N and A stay constant, and the flux stays constant, so B must stay constant. And the magnetic energy density is b squared divided by 2 mu, where mu is the permeability. And when the core is inside of this coil, this where the region where these B fields are, so inside the coil, will be full of this relative potential. So we have mu r, mu naught. And comparing that to the energy density when the core is far away, which is b squared 2 mu naught, this is clearly much less than, because mu r was given to be 10,000, which is clearly much larger than 1. So we can neglect all of the potential energy which the core has at this point, or all the magnetic potential energy at this point. So then the rest is just energy conservation. So at the starting point, the core has no kinetic energy, so all of the so there's only potential energy which comes from this magnetic energy density, and because this is like given to be roughly a long coil, especially as it's superconductive, all the major energy contribution will be all the major field contribution will be inside of this coil. So the magnetic field strength outside of this coil is negligible, basically. So the total potential energy at the beginning is roughly just the magnetic energy density times the volume of this coil. So we get b squared 2 mu naught al, and at the final position when we cut the current, that will be when the energy comes only from the kinetic energy of the coil. And now we simply just have to find whatever B is, and this is simply the magnetic field inside a coil or a solenoid, which you can simply Google. You can derive it using symmetry arguments, and for an infinite coil you can derive it using symmetry arguments and Ampere's law, and that will be simply mu naught Ni divided by L. So you then plug that in there and solve for V, and that's it. Oh. Just checking if... Yeah. So the next problem is a simple celestial mechanics problem. Celestial mechanics. So problem number 5, into orbit. I have to remember to drink a lot of water since I'm talking so much. So 5. So we are at a planet which has some mass m and radius r, and there is a very huge platform of height r where we shoot a cannon, and we want to hit we want to get it to an orbit around the planet, and we want to find the minimum force for this to happen when the cannon has some length L, basically. So well, clearly, for the force to be minimal, we want to find the minimal velocity at which the cannonball can exit this cannon, such that we have a full orbit. And clearly the force is minimal when the energy of that orbit is minimal, since kinetic energy will be transferred into the energy of the orbit, which is quite well known to be minus gm m divided by 2a, where a is the semi-major axis of the ellipse or whatever conic section you have. And clearly a is the lowest when the orbit looks like this. Let's see if I'm good enough at drawing these ellipses. Something like this. So that the semi-major axis is a is equal to 3r divided by 2. So now we can use the energy conservation. Initially, there is some kinetic energy of the ball plus some gravitational potential, and since it's at height 2r, and this will be equal to the energy of the orbit. Clearly the mass of the ball cancels out here, and we can solve for v. And once we have solved for v from this equation, which is like gm 2r minus 1a, and then we can and then we just have to find a force to exert this type of to get this speed within this cannonball. And the force will be simply ma. And now I will write the acceleration like with a big A, since I used A here for the semi-major axis. And the acceleration we can find using kinematic, once again, kinematic laws. So v squared will be 2al, and thus A is v squared divided by 2l, and then we can plug this in, and then we can plug this in, and then we have solved the problem. Not too difficult. Then, problem number 6. The solution is finished, since we have created the ellipse to just barely not touch the planet. I'm just responding to a chat message. We found the minimal ellipse, or the ellipse with the minimum possible semi-major axis such that it won't touch the planet. And since L is notably larger than R, we can just neglect the length here. So like it's simply the cannon is simply a dot here. This would just change the solution just a slight bit, since actually in this case this point would be since at this point will be at a higher potential, but that is negligible. And because of symmetry, everything works out. Since even though the planet will start to rotate, like this is slightly inaccurate, since basically this platform here can intersect with the ellipse at other points, but we are asking for like to just find the minimum possible. And actually it has been told that you can ignore the movement of the planet. specifically in the problem statement. So the trajectory will just stay like this. So this picture is complete. So let's continue. So the roundabout questions. All right. So we basically have a ramp that will go to a circular track in a smooth way, basically. So there is some circular track with some banking angle, so there is like some banking angle with respect to the horizontal, let's say theta here, and there is a ramp that goes smoothly to this circular track. The ramp has some length d and some coefficient of friction mu. You technically are correct, but the corrections are minimal for the last problem. It could technically, actually it could not, because this is yeah, it could technically the trajectory could cut it like this, but the corrections are minimal again. So this is a non-issue. Besides, you can check it what would be the eccentricity in this case. Since both of these will have like foci at the, since both of these conic sections have the same foci or the same focus, it is a non-issue. But anyways, let's continue because I don't want to be here for 2 hours. So d and mu, and what else? And we want that it will, yeah, as I said, it will be a non-issue due to the fact that the focus is the same for the circle and the ellipse. So, like, that is just basic conic section stuff. Anyway, and we want that this block, once it gets to the circular section, will just move in uniform circular motion. And we just want to find what is the maximum value for theta for which this is possible. So if I'm able to vary d and mu, I want to find the largest possible theta. So a block. So first of all, we want to find the speed at which like the I just have to, oh, and this has also radius d. So we could first find what the necessary speed is to be able to do uniform circular motion on this banked ramp. So let's consider, and the banked circular section here has no friction. So we have a block here and some angle theta. There is some gravitational force and some normal force, and we can I'm just wondering if I should solve this in my favorite way, but I guess that's not really relevant here. So then we can consider that this will have some sort of centripetal acceleration, and there's several ways to relate the forces to the centripetal acceleration, but the easiest way and the method used in the solutions is to just project everything onto the plane of the ramp. The projection of the centripetal acceleration is clearly, and the centripetal acceleration is mv squared divided by d, and the projection of it to the, sorry, that's the centripetal force. Yeah, mv squared divided by d, we project it, that's cosine theta, and then because the normal force is perpendicular, then the gravity is the only thing that can project to the plane, so we have mg sine of theta. So we have found that v squared is equal to gd tangent theta. Alright, and then we just have to find what is the speed at which the block will enter the ramp from here. Well, we can find again the acceleration of this block. The acceleration about on the ramp, like projected on the ramp, will come from the friction and gravity. So let's again put some forces. So we have gravity, we have a normal force, and then we have some friction force. The gravitational force is simply mg. N is mg cosine theta, and thus the frictional force is mu n is equal to mu mg cosine theta. So the total acceleration is g sine of theta minus f divided by m, which gives us g sine of theta minus mu cosine theta. Yes. And then we use again the kinematic equation to find that v squared is equal to 2ad, and that'll be 2gd sine theta minus mu cosine theta. Then we can relate these two equations together and solve what condition theta must fulfill, basically. And you can quite clearly see that you will get some equation that is like cosine theta 1 minus mu cotangent theta, and by varying this mu you can and this must be equal to 1/2, and by varying this mu you can do this numerically, you can also do this exactly, but theta, the maximal theta from this will be theta max is 60 degrees. It is also like easy to see, like using physical intuition, it is easy to see that the banking must be maximum when the velocity at which it enters is the maximum, and that will be when mu is 0. So then you get automatically cosine theta is 1/2, and then the 60 degrees is obvious. Oh. So then the next problem. And I decided that I want to do this next problem, like explain from, like I will use a similar method, but I'll do it more analytically and without shortcuts. So let's first talk about generalized coordinates. I don't know how long I will talk about this, but I think this is, especially as this is problem number 7, and most beginners might not know about this, so I think this is good. So typically, we can write the total energy using a sum of kinetic energy plus some potential energy, and both of these, like kinetic energy will be 1 m v squared, and or in one-dimensional case it will be like, let's say our coordinate is x, it's x dot squared, and v will be some function of x. We can generalize this for other variables than just some coordinate, some spatial coordinate. The coordinate could, for instance, be an angle, and you will know that, for example, that for angular rotations, the kinetic energy can be written as 1 over 1/2 times the moment of inertia times that angle changing squared. So I can also write, and also I could have some potential that depends on theta. So we can generalize, use like basically any coordinate we want. So let's assume that we can write our total energy using some generalized kinetic energy and some generalized or effective potential, such that the kinetic energy, and we will use a generalized coordinate psi, basically here, so that the kinetic energy can be written as 1/2 times some scalar m psi dot squared, and this m will be called effective mass, and that the potential can be written as a function of psi, only psi, so it only depends on psi, not its derivatives. Then we can find, and assuming that energy is conserved, we can find the equation of motion using energy conservation. Since energy conservation is just an integrated form of an equation of motion, we can differentiate the equation of motion. We can differentiate the energy conservation to find the respective equation of motion. So as energy is conserved, the time derivative of E is equal to 0. So we just differentiate this sum. So the kinetic energy differentiated will be 1/2 mass. Then using the chain rule, we have 2 times, so the outer derivative is simply 2 times psi dot, and the inner derivative is, so the inner function here is psi dot, so we differentiated it another time, we get psi double dot. And using again the chain rule for the potential term, we get the outer derivative times the inner derivative, like that. So we get that because this is 0, we can cancel out these psi dots, and we get that psi double dot is minus v psi divided by m. So we have a equation of motion. And now what we are interested in is some small oscillations about an equilibrium point. So what would that equilibrium point be with respect to a generalized variable? Well, first of all, because we are talking about an equilibrium point, the acceleration with respect to this variable must be 0. So at equilibrium, so let's write EQ, this is equal to 0. And that happens when the generalized potential has a derivative equal to 0. And at the equilibrium point psi naught. So now we consider slight perturbations around this equilibrium point. So we will consider cases where psi minus psi naught is much smaller than psi. so small perturbations. In that case, I can go back to the total energy and rewrite the effective potential using its Taylor series. And because I am talking about small oscillations, I can write it about psi naught and then ignore higher order terms. So we have the 0th order term, which is simply psi naught. This can easily be set to 0 if you want by changing the potential term, but I will just leave it. Then plus v psi naught, psi minus psi naught. But by definition this is equal to 0. Plus 1/2 v psi naught, psi naught squared, and then higher order terms of psi naught. So we will neglect these. Small is equal to 0. And when we consider this, now the total energy, which is 1 m psi dot plus v psi naught plus 1/2 v psi naught psi naught squared, and differentiate with this with respect to time once again, and the total time derivative is 0 because energy is conserved, we will get something like this. This has a time derivative of 0 because this is a constant. So then we have again something like this. And this is equal to 0. So we can cancel these terms out. And now we will see that this is simply a harmonic oscillation about this equilibrium point. So clearly a solution to this is psi is equal to psi naught plus some cosine, so plus some oscillation around this for omega. Omega squared is equal to v double dot at psi naught divided by m. So now our so this is a generalized formulation for one-dimensional situations. For situations with 1 degree of freedom, this is a generalized formulation of small amplitude oscillations. And now our idea is to try to find some sort of formulation for k and v such that we manage to reduce the degrees of freedom to 1, which we will notice is possible for this situation, and then find k and v such that these two conditions fill out, and then we just find what is the effective mass and the effective potential second derivative. So let's continue. So 7 continues. First of all, we are at a banked track, something like this, and with some angle theta. And from above we have some angle, let's say phi, and from this distance we have some radius r. So we have seemingly 2 degrees of freedom. So we couldn't use our generalized formulation, but we have also other conservation laws which we can use to reduce the degrees of freedom to 1. And the point is that if I think about the block here, it has some gravity and a normal force, and the normal force ensures that there is no acceleration, that there is no force component perpendicular to this banked track. So the total force will point toward along the plane, which means that the angular momentum with respect to this apex point is conserved. So let's say that this entire distance here is L and this is also at some height h. So now let's write the total energy. Well, the total energy comes from the kinetic energy, and as the speed can be written as two perpendicular speeds, there's some oscillation along, there's some speed component due to the oscillations along this plane or the bank track, but there's also the rotation through it. And because those are perpendicular, I can write them as separate kinetic energy terms. So I will have some mr squared plus mr squared phi dot squared. Okay, fine. And then there is the potential energy term mgh. Well, clearly R seems to be the better way to parameterize everything, so let's just write that R is equal to H is equal to R tan theta. Okay. So now we have still this extra degree of freedom from this phi term here, but we can get rid of this using the fact that the angular momentum was conserved here. So what is the angular momentum at that point? That seems to be M L ML R phi. And I will now note what the model solution does, because it's a bit tricky, and I will not do it as the model solution does, but the model solution leads to a slightly shorter solution, so I will explain what it does. The fact is that because this is constant, phi dot I think, yes, because this is constant, and I can write L with respect to R, which is mr squared phi dot divided by, I think, a sine term, like this. No, a cosine term, yes. Like this. Then also this is constant, because theta is invariant. But the point is that this thing in the numerator here is the angular momentum with respect to this red point. So that is what the solution does, is look at the angular momentum with respect to that point. But that is not what I'm going to do. I will use do everything like properly. Okay, so now I can write this phi here with respect to this everything here. So phi is equal to L divided by m mr squared cosine theta, and I can plug this in to the total energy. Actually, there's a mistake here. A good thing that I noticed. Notice how I wrote that the oscillation is along the plane here. So, but R is not at the same direction. This should be L dot here. So L dot. But because L is equal to R divided by cosine theta, I can write this term as R divided by cosine squared theta. Alright, then I can plug this into that to get L squared divided by 2m R squared cosine theta, cosine squared theta, and then plus mgr tangent theta. But notice how this term here is a function of R, and this is a term in the form of 2m r squared. So the effective mass is equal to m divided by cosine squared theta, and our effective potential is this term here. So now we just have to find the equilibrium position and its second derivative. And the equilibrium position was the one where the first derivative was equal to 0. So let's do that. So the first derivative is equal to 0, and we know that the equilibrium position is when r is equal to d. That is given to us. It is originally at equilibrium, but then we give it a little push. So we know that Vd is equal to 0, but this is like minus L squared divided by 2md md cubed plus mg cosine squared theta plus mg tangent theta. So at equilibrium, our L squared md3 cosine squared theta is equal to mg tangent theta. All right, and then the second derivative at d is equal to is equal to L squared divided by 3L squared divided by md fourth. But this is simply 3 times mg tangent alpha divided by d. And now omega squared was equal to this, which we get to be 3 mg tangent theta cosine squared theta divided by d, but tangent theta cosine squared theta is simply sine theta cosine theta, which is equal to 1/2 sine 2 theta, and the rest is trivial. All right. So this was a slightly longer solution, but I think this solution is a little bit clearer because the model solution uses certain shortcuts without telling you. So I wanted to show you how it's done analytically, and I think this method is really good to know, and that is why I used a bit of time for this problem. But let's try to move a little bit quicker, as already an hour has passed and we are only at problem 8. So I think this will be a long stream, but let's see. Luckily I have a lot of water with me here. There's a good question. I forgot to mention this. There is a possibility that in the generalized momentum, this term here happens to be 0. In those cases, whatever oscillation there will be, it will not be harmonic. And thus, everything you learned about harmonic oscillations is useless, basically. You just have to solve the differential equation you get and hope you have some oscillatory term. That is so we and also the double prime can also be negative, in which case you won't have an oscillatory solution, but you will have an exponential solution, which just goes to infinity or negative infinity, whatever. But yes, it's a fair question. What would happen when that term is 0, and that is that it depends. It depends on what the third order term will be. Then you have to take that into account, basically. And we will, but the point is that in most cases this will not be the case. And in certain case, there very well could be a problem at a physics Olympiad where the third term is not negligible, and you would have to solve the differential equation. But that means that the differential equation has to be easy to solve, but it's not always easy. But let's continue. I want to sleep today, preferably. Anyways, so problem 8. Again, it's a really easy problem if you know what you are doing. But for a beginner, relativity isn't easy. So 8, atom smasher. So we have a alpha particle which has 2 neutrons and 2 positrons. And then we shoot a neutron at it at some speed v, and we want to find the smallest possible v such that after the collision all of these particles will be unbound. So this is a simple collision problem, but it isn't as simple because we have a lot of degrees of quite a large degree of freedom here. Like how will these particles like what will the speeds be and so on. Well, the first thing is that we really don't care about v right now. We can solve for it later because if we know the Lorentz factor gamma, which is 1 over 1 minus 1 minus yes, we can solve for v later on, basically. And the first thing to note is that the initial energy, or the energy of this system, and I will use unit c is equal to 1. So mc squared will be just m, for instance. So the total energy of this system is the rest energy of this alpha particle at rest, which is given to be m alpha, and the total energy of this neutron, which we can find using the Lorentz factor mn. And clearly, the higher gamma is, the higher v is. And looking at this equation, the higher the total energy is, the higher gamma is. So at the final position, so after the collision is done, we want the energy to be as minimal as possible. But there is, of course, like quickly you could say, oh, that's when all the particles will be at rest. But no, we have to consider the conservation of initial momentum, because for example, for this alpha particle, this neutron here, we will have the 4 momentum norm, which just relates the energy to the rest mass and the momentum, and this is for the neutron only, what I'm considering here, except that the momentum of this neutron is the momentum of this system, clearly. But E is gamma mn as here, so I can simply solve that m square, p squared is simply gamma squared minus 1 mn squared. So I want to find the minimal possible energy after the collision, using the condition that this momentum is conserved. But here's a very, very nice trick to do this. Let's go to the frame where the center of mass is at rest. Basically, let's go to the frame where the total momentum is 0. In that frame, the total energy is minimized if all the particles particles are at rest at the same time. This is clear. And just as in classical mechanics, if the energy is higher in one frame, it is higher in every other frame. So this minimizes the energy in all of the frames. So then we go back to the lab frame, so we such that the system of particles has the certain momentum, but because they had the same velocities in the center of mass frame, they have the same velocities in the lab frame. So the frame where all of these particles are moving at the same speed, at the same velocity, minimizes the energy. And because all of these particles move at the same velocity, I can think of this black box here as one particle of mass m is equal to 3mn plus 2mp moving at some speed v, such that the total momentum is the same. And as the total momentum is the same, we can once again use the 4 momentum norm to say that the E squared is equal to P squared, which is the same in this case as it's before the collision because momentum is conserved, plus m squared. So now I have this relation here, which I can plug in here, and I have this relation here, which I can plug in here, and then I have an equation where I know everything else except gamma, and I can solve for gamma. So I will get something like m alpha plus gamma mn squared plus is equal to gamma squared minus 1 mn squared plus m squared. And then you just solve for gamma. I won't go through the steps here, but it's something like this. And when you know gamma, you can solve for v using this Lorentz factor here. And we actually wanted v over c. And then we are done. Okay, next problem. Dying light. This is actually a very easy problem, but it's not entirely trivial what complex index of refraction means. But just as we realized last time, k is equal to 2 pi n lambda, and now we can use the fact that the phase, as I said it previously, because it's proportional to cosine kx minus omega t, I can actually write this as the real component of E is equal to I kx omega t. And this is like the electric field of the wave. And now we can make sense of what this n does. So we have the electric field, or the complex electric field, is like some amplitude ai kx omega t, but now n is some n is like 1 plus ia. I'll use the same notation as in the model solution, where a is like 1 times 10 to the negative 6. So and we can also write this using the old wave vector, which was just nk. So then we can easily write this as 1i. Then we have kx minus omega t plus I times IA, basically. and this is simply I kx omega t e to the minus, oh, there's an x missing, minus a k as well. So simply what the negative component does is tell how the energy is dissipated. The electric field gets smaller, its amplitude. And because the amplitude of the wave is now this, and intensity is proportional to a squared, we have that IF is simply I naught a minus a kx. And then we can solve for the x, at which case IF is whatever. But that's about it. I have nothing else to add to that problem. It's very well written. Alright. Then the motorized pendulum 10. So we have some pendulum here which is able to provide some torque. There's some axle connected to a motor which can provide some torque to this. And the torque is measured with respect to this axle point here. And the torque given is 1 plus cosine theta divided by 2 is equal to T naught. And now we want to find the case where this mass is extremely sensitive and cannot tolerate high speeds, or basically any speed at all. So we want to find what T naught must be such that this motor is able to lift this 90 degrees. Well, clearly the limit here is well, looking at the torque here, the smallest torque which this can provide is at 90 degrees. It's tau naught divided by 2. And the highest torque given by this mass is given when it's also at 90 degrees. So the limit is when the motor is just able to keep the mass at a 90-degree angle. So the torque provided by this by gravity is simply mg sine theta. And because we are lifting it slow, we want that tau theta is always equal to mg sine theta. So then we have 1 plus cosine theta divided by 2 tau naught is equal to mg sine of theta. I forgot, of course, there's the length here, like this. And thus tau naught is equal to mg L sine of theta 2 divided by 1 plus cosine theta. And now we notice what I just said. The numerator here is at its largest when theta is equal to 90 degrees. And similarly, the denominator is at its smallest when theta is equal to 90 degrees. So that is the limiting case. So we get that tau naught must be at least 2 mgl. So the minimal possible tau naught is equal to 2 mgl. Nothing too mysterious. Then we have the then we look at the situation when the motor gives some maximal possible torque all the time, and then we just want to find what is the minimum possible value of tau naught such that it reaches 90 degrees. This is also relatively trivial. We just want to make that the motor is able to give enough work to counteract gravity. So the total work done on the done on the mass here. So the differential work done to the mass is the total torque on the mass d theta. And the total torque on the mass is the torque from the motor minus the torque from gravity. And then we just want to make sure that that this is non-negative to be when integrated from 0 to 90 degrees, because we want to ensure that that it can reach 90 degrees. So we basically just get that the integral from 0 to 90 degrees of tau theta minus mgl sine of theta d theta is 0, technically also larger than. And then you can just do the integration. It's not that difficult. You get that tau naught is equal to 2 divided by 1 plus pi divided by 2 mgl. An interesting question in the chat. For the dying light problem, can we not write the the problem you have with that is we want that phase increases when x increases. What I'm talking about is that why is there no minus here, basically. And the reason is that we want that, or why cannot you write that this is minus? The thing is that we just want to ensure that the phase increases as x increases, since it's traveling in that direction. That's basically the point. All right. And then we go to the problem number 12, which is now if we go back to the first problem, but now we are given the maximal speed it can tolerate. And now we want to find what is the minimum possible value of tau naught. And in this case, this is a good example of a perturbation method. We were given the ideal case, and as v is basically small in this in the given problem, we just consider a slight perturbation to our original solution. So and furthermore, the idea is now that because it can have the block can have some velocity, we should do it in such a way that we give it the maximal possible speed, which is the v given, such that when we let go, it will continue to 90 degrees, basically. And then we just want to find what is the minimum possible tau naught. So we now consider a perturbation to our original solution that tau naught is that 2 mgl minus some slight perturbation epsilon. And using the small and now near the 90 degrees, because we have because v is small, we have to let go near at some position near 90 degrees. That the torque, which was 1 plus cosine theta 2, and now theta is like 90 degrees minus some delta, again some perturbation. We can approximate this using the Taylor polynomial to be 1 plus delta divided by 2 tau naught. And this was not what tau naught was, this was what tau, the torque from the torque from the motor was. Alright. And now we just have to find the point or the angle at which point the gravity starts to overpower the motor, and that we can calculate from just setting these two finding at which point t theta is equal to mgl, which is roughly the torque from gravity at near 90 degrees. Sine near 90 degrees is basically 1. There will be only second degree corrections. So we do that, and we find that delta is equal to epsilon to mgl. And from this point onward, the gravity will do more work than the motor, and we want that this total work done is only enough to stop it at 90 degrees. And because we have done these linear approximations, the work done is approximately linear, and thus the net torque from wait a second, I'll have to just check that I've done everything correctly. Yeah, we have done some linear approximations, so thus the net torque is also linear. How it's done in the model solution is that the net torque is from gravity basically. Is approximately minus mgl delta in this case. There is a because at this point tau naught was we remember our approximation from here, we plug this here, and then we neglect the higher order terms, so we only get this delta here. And now we just find integrate this from this to 0 basically, to get the total work done, and we set that equal to 1/2 mv squared is equal to the total work done from this point on, because the mass starts to decelerate, and the work is simply from that epsilon to mgl to 0 of mgl delta d delta, and we will get epsilon squared divided by 8 mgl, and now we can solve for epsilon, and now we plug it back to this. So the point is that I didn't like give you more information than the model solution here, but the idea is that this is an example of a perturbation method. So we have solved a case which, or we have a case which we cannot solve exactly, or we may be able to solve exactly, but it's too much work. So we consider a idealized an idealized situation which we can solve exactly, and then consider a perturbation to that solution to find an approximation for the situation we are dealing with. So now the idealized situation was that motorized pendulum 1 problem. And now we consider, in the motorized pendulum 3 problem, we consider a perturbation. And these perturbation methods are really common the further you go to physics, especially like at quantum mechanics. So in this case it was just simple as saying that the total torque we need is slightly smaller than in the idealized situation. And of course, as stated in chat, this is doable using numerical methods, using the same idea basically, but not considering a perturbation, just using numerical methods to calculate the integral basically. That's fine as well. But I really like this method given in the solution because this is an example of a perturbative method. Anyways, then gravitational oscillations. This problem was quite funny because there was so many clarification requests asking whether or not we have made a mistake, because there is, for some reason, we have given a charge distribution of a conductive ellipsoid when we are talking about a gravitational disk. But no, that was intentional. The idea is to combine two very common ideas, not very common, but well-known ideas. First of all, is to note that there exists an analogy between gravitation and electricity or electric fields. Gravitational fields and electric fields are the same as long as you consider only like yeah, maybe I should just write. So the force in gravitation looks like this. The force for in electricity looks like this. These are analog. These are basically the same equations. The only difference is that the only difference is that this force is always attractive, when in this case it's or rather I should say the difference is that in this case, when the masses are of the same sign, then the force is attractive, but when the charges are of the same sign, then it's repulsive. So, but the point is that the force is analogous, and thus we can convert electric configurations to gravitational configurations and vice versa. The second well-known idea is that you can consider the charge distribution of a flat disk as a limit of an ellipsoid. And thus we have given you the charge distribution of an ellipsoid to find the charge distribution of the flat disk, and then consider the change the electric situation into a gravitational one using the analogy. And that's what we are going to do. So in the first situation, we just want to find density distribution of the disk, basically. Since we are asking for numerical answers, we are specifically asking for a specific ratio, but we just want to find rho, basically. Well, as stated, let's first find the charge distribution of the electric case. So we have an ellipsoid. It looks something like this. Like a potato, basically. And then we consider that this radius here is equal to 1 because we want this to be a disk of constant radius. But then we let this distance here, this distance c, to go to 0. So we have our that sigma is equal to q 4 pi abc, and we set a equal to b equal to r, and then we consider c is equal to 0. And also we have to consider the case where x squared and we want to find the distribution with respect to the distance from the center, and that is this r here. So we consider these and apply them to the given equation. Okay, so we simplify. First of all, a and b were equal to r, and here we can do some simplifications. Again, a and b are equal, so we get r squared divided by big R squared is equal to big R fourth plus 1 minus r squared divided by r squared divided by c squared. Something like this. Let's check. And yes. If you are wondering where this equation comes from, it's that the equation for an ellipsoid looks like this. And from this we can solve for z squared over c squared and plug this here. Alright, and now we just consider the limit of this. In the limit when c goes to 0, this term will become negligible. You can show it more thoroughly if you want, but so asymptotally we have 2 pi r squared c 1 minus r squared c squared minus 1/2, and now we notice that these cancel out, so we finally get that this is equal to q over 4 pi r squared 1 minus r squared divided by r squared minus 1/2. And the point here is that because of the electrostatic analog, we know that electric and gravitational fields are analogous, and thus electric charge density is analogous to mass density. But now we have this surface density, but we are given that our disk has some sort of height, h. And I almost forgot. At this limit, we have squeezed together the top and the bottom side together, but this surface charge only gives you the surface charge at one side. But now we have squeezed the two sides together, so they must add up. So the actual sigma is equal to Q for 2 times sigma naught, which is Q 2 pi r squared. This is actually not important, because what I was going to say is that because we have this small thickness here, then the mass density is simply the volume density divided by h. But we know this mass density here, we just convert analogously to here. So we have that rho is equal to h sigma m. So the only thing we have to consider is that the charge is analogous to the mass. So if the mass of the disk is m, then we have that rho is equal to m2 pi r squared, 1 minus r squared divided by r squared, and it turns here should be an equal sign, and this should be h, like this. And now you will notice that because we are looking for the ratio, this will disappear. But now the ratio is trivial to calculate. Alright. Then 14. Now we want to find how much mass is there near the outer rim. And this is simply an integration. Nothing interesting here. So I will just like write that total mass is equal to the surface density integrated by dA. But if we think about a small ring here of radius r and width dr, then the surface area will be like pi r squared, r plus dr squared minus pi r squared. But from here we get that the pi r squareds will disappear, so we get 2 pi r dr minus plus pi dr squared. But because dr is small, this is negligible, so we have that this is our dA, which we just plug in here, and our sigma m was rho divided by, actually there, I have to check what I wrote here. Yeah, sorry, this was wrong. I don't know what I was thinking. This is rho times h, sorry. And so this h here should be here. Right. And now we will have that this is simply that rho r h 2 pi r dr, and we were asked to integrate this from r minus epsilon to r, and then you can do this using Wolfram alpha if you want. Nothing too terribly difficult. And then to the problem number 15, and now we want to find the perpendicular gravitation. We want to find the period of oscillation at some distance from the center. So for this we can use, and we drill a very small hole first of all. So let's look at this. So we look at some situation from the center R, and we drill a very small hole here, and then there is some oscillation here. And for this we want to find the perpendicular perpendicular component I don't understand what the question in the chat is. This situation is still about the disk. We are not looking at ellipsoids anymore. The only case where we looked at ellipsoids was this particular case when we were looking at what the density of the disk would be, the density distribution. After that, we only look at the disk. We don't care about the ellipsoids anymore. The ellipsoid was only to help you to calculate the respective uh, the because we want a disk such that the so if you want more reasons for why we are interested in this particular problem is that we want to find the density distribution of the disk such that the the gravitational field is perpendicular to this disk. If this disk has a constant density, then there will be some pull towards the center as well. But because we know from electrostatics that conductors have perpendicular electric fields, then if we consider what the charge distribution of a conductor is when it's flattened into a disk, we can find such a density distribution of a disk such that the perpendicular gravitational field is such that the tangential gravitational field is zero. So we are making basically a planet, a flat Earth planet, in such a way that you will only feel gravitation downwards, so you won't be pulled toward the center of the disk. And we do that using this electrostatic analogy. That is why we are looking at this ellipsoid, because calculating yes, basically, because h is very much smaller than r, we then consider that we first flatten the disk entirely, and then we stretch it a bit to accommodate for the height of the disk, to give it a bit of height. But because h is much smaller than r, it's the changes are basically to the gravitational field are negligible for our purposes. But yes. So let's consider this drilled hole here. So we want to find what is at some point z from the center, what is the gravitational field. And for this we can consider Gauss's law. So if we consider a very, very thin surface here, so a very, very thin Gaussian surface here, with some area ds. You can also consider the Gaussian surface to be at a constant radius from the center as in the previous part, like this. It has some surface area dA. Then we just consider Gauss's law for gravitation in this case. And in the electric case, Gauss's law looks like this. Is equal to Q over epsilon naught. But now we consider the analogy, and because the gravitational constant is equal to in the equations is analogous to 1 over 4 pi epsilon naught, and actually minus because of the change in direction. Same signed. So positive charges repel, positive masses attract. So that is why there's this minus. So then the epsilon naught is analogous to minus 4 pi g, which 1 over epsilon is equal to 4 pi g. So we get that the Gauss's law for gravitation looks like this. And now we just apply Gauss's law for this small disk here. The flux we consider, so this has height z in both directions, so this is 2z. Alright, so there is only flux to above and below, so we have 2g dA basically, and the total mass inside is we have calculated rho, and that is rho dA to z, and dA's cancel out, and we find that g, so the gravitational acceleration is equal to minus 4 pi g rho z. So we get the equation z double dot is equal to 4 pi g rho z, and thus the angular frequency squared is simply 4 pi g rho, and now we have basically solved the problem. T is equal to 2 pi omega. Then liquid lenses. So it seems that my 2-hour expectation was not very realistic, as I've been talking for almost 2 hours now, and we are still not even halfway through. Maybe I should pick up speed, but let's see. So liquid lenses. This is a nice problem, but I don't like this particularly well due to the math. It's not even math bash. It's just annoying for me. But of course you have like computers and such, so you can skip the math if you want. I will provide now. So in this case we have a lamp above a bowl of water which is rotating. So this is rotating, and thus the surface of this water here will rotate. And we are shooting photons with this lamp here downwards. And we are asking that if the rate at which these photons come from, what is the rate at which they bounce from this? And the reason why this is not simply the same rate is that if we look at, for instance, these photons here, they will reflect and bounce again before they will leave. So we first have to find the shape of this curve, and I will show my favorite way of doing this. There is this force way, which is used in the model solutions. There is a way to do it with pressures, but I like to do this using a non-inertial frame. So let's go to the frame which is rotating. No, let's first consider a simple fact about liquids. Liquids cannot sustain, like if you have a liquid, it cannot at an equilibrium, at a static equilibrium, it cannot sustain shear forces. So if this parcel of liquid here suddenly has a force F to the right, the liquid will start to move, and then you break the equilibrium until the pressures like cancel out this force. What does this mean for the surface? The surface here cannot have any forces parallel to it. And if it cannot have any forces parallel to it, it means that it only has forces perpendicular to it. And if we consider that force is the gradient of potential, then this means that this surface here is equipotential. So it is at constant potential when it is a static situation. So now let's go to the non-inertial frame where this liquid is static, is at rest. Then this the shape of this curve is at a constant potential. But what are the potential terms? Well, there is a potential from the gravity, but there is also a potential from the rotation, the centrifugal force. The centrifugal force, which is equal to m omega squared r, is trying to pull everything to infinity. So this will have so this centrifugal force will have a potential which is equal to 1 over m omega squared r squared. Basically, it tries to take things to infinity, and you can check that this the centrifugal force comes from this back. Alright, and this is a constant, and with a proper and as we know, we can always scale our potential energies in such a way that the potential will be 0. So I can set this to be 0 for this surface. And how does this work? It means that I set the gravitational potential to be 0 at this level, like here, and then at r equals 0 the potential is 0. So then we are done. So now we know our coordinate system like this, and then I simply find that y is equal to is equal to r squared is equal to r squared omega squared divided by 2g. So now we have found the shape of this, and this is a parabola. This is notable because using the properties of conic sections or the optical properties of parabolas, any vertical ray that comes through this must reflect through the focus. And thus, when it reflects through the focus, it must reflect back vertically again. This means that there cannot be any rays which reflect 3 times. It is either 1 time or 2 times. And how do we find this focus? There is actually a very nice way of doing this, and and I will leave. No, I won't leave this. And it is to use again the fact that all these vertical rays will reflect through the focus, and that is that I can the ray which comes like symmetrically to the symmetrical center will just clearly reflect back. So the focus must be somewhere on this vertical line. But then I can consider the ray which reflects at the point which is at a 40-degree angle from the horizontal, and that will clearly reflect horizontally. So thus the focus must be here. So the focus must be at the height at which the parabola has such a gradient that the respective angle is 45 degrees. And that is easy to do. The derivative of y must be equal to 1, and that immediately gives you that y is equal to, so the height of the focus is equal to g is equal to 2 omega squared. Alright, so now we have done the setup. Now we just want to find the region at which all of these rays will reflect twice. And it is clear that it won't reflect twice if it's too close to the center. And we know how these rays will reflect. So at the limiting case, you have a ray which goes through the center at one point. So when it has reflected, it goes through the center and then just barely misses or touches the edge. And all the rays which are inside of this region, defined by these rays, will only touch once, or reflect once. So let's find the radius of this region. So we know that this line here passes through the focus and the edge. And the radius of this whole thing was capital R, which was given. Thus the gradient is its highest point is this r squared omega squared term, r squared omega squared divided by 2g, and it starts from the focus, which is g over 2 omega squared. Oh, and the I'm just doing a reality check. No, everything's fine. And the horizontal length for this is r. So we have r omega squared 2g minus r minus g 2 omega squared r. That is okay. And then we can find the equation of this line. And that is easy to do in our coordinate system. That is simply g2 omega squared plus our gradient times x, or r in our coordinate system, omega squared 2g minus g 2 omega squared r times r. And now we just have to find at which point this intersects the parabola once again. And for this you can just put this equation here and solve the second, the quadratic equation. The other point where it will intersect is at r is equal to g squared r omega 4. I won't go through the entire derivation. Alright, and thus the proportion of the photons which will only reflect once are those within this blue circle when looked from above, which has this radius here, which I will underline with blue as well. And thus the ratio is n is equal to 2 minus g squared r omega to the fourth. Alright, then problem number 17. I feel like the solution, the given solution for this problem is a bit confusing. I will spent some time to explain this in detail. So, problem number 17. So first, let's prove, as given in the so we have a chamber of a gas with particles which have like charge Q, and there is a constant electric field. And we neglect the interaction between the particles, so we can basically neglect the electric field of the particles themselves. And we are given that in this initial case, the pressures at each side are these. And then we are asked what will be the final pressure when we take off the electric field and still neglect the electric the interaction between the particles, so we neglect Q basically. Or yeah. So it is just the model solution is just basically stated that the that P will be that the pressure gradient will be exponential. I want to prove this, and I will prove it using two methods. So the first of all is just to find the electrostatic equilibrium. We consider a thin slice here, like this. This has some thickness dx and some area A, and this must be in some because we are looking at a static situation, this must have zero net force. So there is some pressure P on the left side, and there is some pressure P plus dP on the right hand side. So the total pressure from the total force from the pressure is dP times A, and the total force from the electric field is the total charge within that volume, which is some dq times E. This dq is simply some n dv qe, where n is the number density. The number density of the particles, of the gas particles. And number density is just units of amount of gas particles in a given volume. And dV is ADX. Alright. But now the problem is that n is dependent on x. But for this we can use the ideal gas equation, which simply states that P is equal to nKT, where K is the Boltzmann constant and T is the temperature. And we are given that the temperature is constant, so we can plug in n from here. So we get that this is equal to PA dx QE divided by KT, and this is a separable differential equation. We get that, and notice that a's cancel out on both sides. So we get that dP divided by P is equal to QE KT dx, and we can basically integrate this to find that P is equal to some P naught E to the Q, some let's just put some constant E minus E Q E K T X, and this proves that it's exponential. And we are saying this. But there is a very nice way to come up with the same equation at the same time, and that is using the fact that we are keeping this at a constant temperature. So the energy distribution of these gas particles here abides by the Boltzmann distribution. And the energy, the potential energy of any amount of gas here comes from the electric field. The potential energy is equal to QEX, basically. And the probability that the pressure is proportional to the number density, which is proportional to the amount of particles at any given state, which is proportional to the probability for them to be at that state, which is given by the Boltzmann distribution to be this is not true. This is minus QEX. The potential energy goes lower when you go along the electric field. So the Boltzmann distribution gives this, which for our potential term gives this. So P is equal to sum A equal to QE KTX. Voila. And now you can deduce, we want these boundary conditions to be fulfilled, and this gives you that P naught is equal to x minus r ln squared divided by 2 as given in the problem. But now, I just wanted to showcase these two methods to prove that it is really exponential. And now, how do we find the final potential, final pressure? Well, in the final state, when we take off the electric field, the gas will still abide by the ideal gas equation, which will now which I can write in this form. So it actually just depends on the total amount of particles. But using this equation, I can find the number density before the setup. So n is equal to P divided by KT, and Nx is equal to Px divided by KT. And thus I can find the total amount of particles to be n is equal to integration of nx per volume, and this basically proves to you that when I plug this into here, you will plug this into here, we have PV is equal to Px n KT dV. These cancel out, and this gives you that P final is and the total volume, of course, is 4 over 3 pi r cubed, and you just have to perform this integral, and that is done in the solutions. I just wanted to explain how you get into this, because I don't really, the solution is very brief. It just says that it's exponential because of hydrostatic equilibrium, and it just states that, oh, the final pressure will be the average pressure. Alright, but why? That is what I wanted to explain to you. The rest is just math. So now, problem 18, ping pong. This was one of my suggested problems. Sorry, I just got a message. Okay, so problem number 18. Yeah. So in this case, so ping pong was one of my problems. I came up with it when I was playing, well, ping pong, and originally, so yeah, what we have here is that we want to find that we have this ping pong table which has some length d up to this point, and this net has some height h, and we want that this ball, which starts from here, bounces once on the table and then goes over the net in some way. And we want to find what is the minimal possible starting speed when the direction of the ball, the direction of this velocity can change during the bounce, but not the magnitude of the velocity. When I originally came up with this problem like 2 years ago, yeah, something like that, I was wondering what is the minimal speed if I don't allow for the direction to change, but that turns out to be just really math heavy. Like, I don't remember if there was even an analytic solution to that, so it had to be done numerically. Anyways, it was just bash, but then I realized that if I allow for the angle to change, then this becomes a much more nicer problem. And I will explain my solution, and that is to use the envelope curve. So let's first consider a simpler case. What would be the smallest speed to just go over the net? One way to find this is one way to do this is to consider, or actually to admit, to not make these variables too tricky. I will now use, or I don't want this to confuse us later on. For this one zero bounce case, I will only consider, I will use these capital variables. Okay, so what would be the minimal speed to go over this net when I am here and there is no bounce? Well, one way to do this, there's several ways to find this, but one way to do this is to find all the points you can reach with a given speed, and then to find at which given speed that region has its boundary at here. Because if I increase the velocity, then the boundary will grow larger, so it is inside the region, or if I take it smaller, then it will be outside. So, how could we find this? Well, first of all, the trajectory. So if I launch this at some given angle alpha, the trajectory is easy to find using the classical kinematics equations, vt cosine alpha, and y is equal to 1 minus is equal to this, and then you can solve this to give that y is equal to minus gx squared 2v squared cosine squared alpha plus x tangent alpha. And the key insight here is that if there exists a point pair xy which is reachable with some angle alpha, then there exists a solution for alpha such that this equation is true. So how do we find the envelope of this? Well, the mathematical insight here is that this 1 over cosine squared term can be rewritten as 1 over tangent squared alpha, so a trigonometric identity. If I plug this into my equation, I will get a quadratic equation with respect to tangent alpha. And tangent alpha, depending on the launching angle, can have any value, any real value. And thus, if there exists a solution, a solution pair xy, then the discriminant of that equation or if there exists a respective alpha for which this equation is true, then the discriminant of that quadratic equation must be non-negative. So to make this a bit neater, let's call tangent alpha to be psi. So then I can plug this in here and get a second order equation with respect to, so this is just math. All right. And so for any given x and y, so if I can reach any position, then the discriminant will be 0. And now I just copied this from the model solution, so I should change this to be y, because I am doing this slightly differently than in the model solution, because I want to derive the envelope curve to you, because we will use it later. So this is g squared x squared. Okay, and if I set the discriminant to be non-negative, you will get that you will get an equation for y which looks something like this, and I will check this because I don't want to do the math right now, because we have already passed, we have still a lot of problems to go. So you will get that this is equal to v squared 2g. So these are all the points you can reach. These are all the y-x pairs that fulfill the original equation. So it's actually a parabola. And we just want to find that at for which speed v this parabola goes through this point. And this is easy to solve. I won't do it right now. You will get that v is equal to gy is equal to gh plus g d squared plus y plus h squared. All right. And now my idea is that because the speed is the same before and after the bounce, then if it bounces at a distance x from this table, edge of this table, let's say here, then the minimal speed at which it could have come from this point here and also go through this point here are both given by this equation here. And it of course has to be maximum of those two. So the minimal speed with respect to our x is the maximum of, well, is to go over the net from that position. The height is still h, but the distance is d minus x. And to reach the edge of the table, it's simply gx. Something like that. And now we notice that this term increases with x, and this term decreases with x. So thus the minimum of this function is when these two terms are equal. And you just set these two things to be equal, and then you get that the respective x is equal to d squared 2 over d minus h, and then you plug that into either this or this, and you get that v1 is equal to d g 2d minus h. Alright, then we basically use the same idea, but now we think about what did we just prove. Well, it is well known that the maximum range on flat ground happens at 45 degrees. So the minimum velocity or the optimal curve to reach this point happens at 45 degrees for the first bounce. Well, we can generalize this thing for many bounces by saying that all the first bounces have to be we'll have to get the ball to be as close to the net, because at the last bounce it has to go over the net and it has to increase the angle, possibly. So to get the final minimal possible final bounce, you want to have the maximal minimal possible distance from the net. So basically the final bounce, so if x is the distance from the net at the final possible moment, so we have many bounces. Here is x, and then we go above it. Then the starting speed is equal to, or the starting speed has to be at least equal to. So we want this x to be as small as possible, and thus we want to have all the previous jumps at an angle of 45 degrees. And the range for these bounces is v squared over g, as we can find, for example, from the envelope curve, let's say. So the final bounce is at a distance of d minus nl, and because Vn has to be at least, so at the optimal case we get right below the net, in which case that this Vn is at least larger than 2gh. So if we reach the net in n bounces, then the minimal speed will be whatever this is. So as long as so we will find the equilibrium, which I'm talking about in the problem statement, when d minus nl is smaller than 0, basically. So we would be able to go here. And plugging in our values for v and for L, I can find that n has to be larger than d over 2h for this to be possible. And we can calculate this to be equal to 4.5 roughly. So this means that the big N described in the problem statement is 5. So with our given values. So for 2 to 4 bounces, the minimum possible starting speed decreases, but after the 5th bounce it reaches its lowest possible speed. Alright, so now let's consider the case when we cannot reach the net in n bounces. Well, again, the final bounce will happen at x equals d minus nl. And the final, and I just have to yes, to get the final bounce to be at least this distance x away, is again, we can calculate from this range equation here. V squared is equal to Lg, but sorry, I have to close my door. So this is for one bounce. So for many bounces, so this range, as stated, is equal to d minus we can calculate plug in L from this equation to this equation, so we get that the to get the ball to get the ball at the last bounce at the such that the last bounce is a distance x away. This is the speed for that, and again we want the final speed here to be equal to this for the minimum, and then you just solve whatever Vn is, and then you calculate Vn minus 1n. So that's the idea. Okay. Yes. I just had to check. So then, the envelope of light. In this case, we have a light in some ceiling, in some cylindrical shell. There is a light source, and this will draw a hyperbola on the wall, and we are given some information such that the hyperbola will start at some point here, and we want to find the horizontal distance d. And the reason why this will be a hyperbola again is that the point should be here. So we are given this height here, and we want to find this distance d here. So the reason why this will be a hyperbola is because this this cylinder here will define a cone, and this wall here will inject the cone, and the light, the shape of the light will be the intersection, or the boundary will be the intersection of this cone and this wall. So it will be a conic section, and in this case it will be a hyperbola specifically. So now we just do some some conic section math. So the first one is that the eccentricity of a conic section can be theta p, and I have to be just careful with how I define my variables, and theta c. So the eccentricity of the cone can be calculated as such. This is either the definition or not. And because theta p is equal to 90 degrees, this is simply 1 over sine theta c for our problem. But we can also write it using a hyperbola can be written, for instance, in this form. So x squared over a squared minus y squared over b squared is equal to 1. So if a and b are known, the eccentricity can also be calculated as a squared plus b squared divided by a. Okay, and thus we can find what sine theta c is, and thus we can find what tan theta c is. And tan theta c turns out to be a over b, but looking at our figure, it will also be HOD. Yes. And then you can calculate it. So it was just basic conic sections once you realize what you are doing. Okay. Then let's see. So question number 21. Under the lamplight. This once again is quite a mathematical problem, but yeah, there's other ways to solve it. Like, if you know conic sections, this is not the only way to do it. There's many different ways to find what you want here. That is, I just think this is the final the model solution is we need is like 2 lines using these. There's also other geometric ways to solve it, but yeah. So 21 is under the lamplight. For this, I don't have anything else. The idea is that the circle will have some different area because the light will start to bend. So so we have a lamp here, so there is some light forming a cone here, and because there is some so the refractive index is going up, and by Fermat's principle light goes through the path which minimizes its time, and its velocity is going lower the farther down it is going. It starts to bend downwards, so you will have something like this. And now you want to find basically this curve to find this final radius. And the way to do is to use Snell's law, basically. So if you Snell's law says that n1 sine theta 1 is equal to n2 sine theta 2 for any part, but I can divide this liquid into many different layers of very thin layers of height dy, and they will have some ny, and thus, and because this is a constant, I will get that n sine theta is some constant, which I can find from the initial conditions. So we get like 1/2 for this particular case, and with some and the way we define things is that we have our coordinate y and we have some x coordinate, then and theta is measured with respect to the normal. Thus we have that dx dy will be I'm just checking, it should be, I guess, tangent theta. And then you just want to rewrite this in using the relation between tangent and sine. You can write this in a form which gives you that an equation where you have a derivative and n is a depends on y, and thus you get a differential equation. I won't go through all the math. You have the math at the model solution. Basically, at the end, you will get that dx dy is equal to 1 over 2 plus 4y squared minus 1. So this is the same thing. 4y squared minus 1. Yes. Okay. And so that was, again, just math. Then 22. For this, I don't have, again, much to say. This cannonball was also one of my problems. Originally, I designed this problem for the Nordic Baltic Physics Olympiad, and the ping pong problems and the cannonball problem formed an entire problem, basically. So I think the first problem was to find what is the distance. So in the ping pong case, it was without bounce to go over the net, with one bounce to go over the net, and with n bounces to go over the net. So those were part A, B, and C. And then part D was that if you have a cannon going over a wall, what is the maximal distance and what is the minimal distance, was part E. So that was like my original suggestion for like Baltic Physics Olympiad. But because this is quite bashy, these problems, I think they are a better suited for OPhO, so Online Physics Olympiad. So how do we solve this cannonball problem? Well, this is actually probably the easiest way to do this is to just use some graphing calculator and find what is the maximum and minimum distance. The full solution is similar. The idea is that 45 degrees would be normally the largest range, but now it crosses through the wall, so it has to go above the wall. I want the model solution, I think, is great, or is clear enough, but the idea is that clearly it has to go just above the wall. And the optimal angle for the maximal distance is when alpha is the lowest, and the minimal distance is when alpha is the largest. And as we did previously when we were finding the envelope curve somewhere back here, we can use the same method because psi here was tangent alpha. You can solve from this envelope curve equation, you can solve tangent alpha such that it goes through this distance. I think these were d and h, and this turns out to give you that psi has two different values when you solve the quadratic equation. And as stated, the larger angle will give you a lower value, and the smaller angle will give you the larger value. So from the range equation, you can just get like the range equation, I think, has sine theta in it, but you have the tangent tangent alpha here. So using the range equation, so basically the envelope curve, you can get this. So this is for x max, and x min is the same except with the larger root. Alright. And then we have the filament question. Filament 1 and filament 2. Right. Well, filament 1 is rather easy. The idea is that we have this sphere. This sphere, like this. But there's a small flat top here. And there is another small flat top here. And due to symmetry, when I plug these into some electrodes and draw some current, the equipotential lines by symmetry will be just spheres like this. And each and because the current flows perpendicular to these are simply in parallel. So then we can use the fact that R is equal to rho L A, so something like this. So a differential R is rho dl A, and in our case, when we have some angle, polar angle from the top, phi, like this, then A is simply 2 pi r sine theta times t, and our dl is r d phi, and thus we simply have that r is equal from this angle to this angle, which I will call phi initial and phi final. Then we have our rho r d phi 2 pi r sine phi times t, and you can find phi I and phi final using trigonometry, basically. But that's it. So 24, I will just outline the idea for so I have to drink something. Integrating in Cartesian is not incorrect. You will but you have to take many things into account, basically. So it is very easy to make a mistake in Cartesian coordinates. Integrating in any coordinate system is fine. You can make your own coordinates up, but you have to be careful. No. Anyways, 24. It's basically the same-ish problem, but we use some. So we have the same case, but now we have these flat spots here, 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 and also behind it, and here. And we plug in some current here and take it out from here. And we want to find the effective resistance of this setup. Well, the idea is that we can use a superposition here. And the first idea is that we plug in some current from above and take it symmetrically from everywhere. So we take it from here, 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 here. But again, the current which passes through some disk like this at some angle phi is the current which is taken away from the rest of the sphere, and that is by inspection is 1 plus cosine phi divided by 2I. So then we can solve for the current density, which just follows tangentially along the sphere, is the 1 plus cosine phi divided by 2I divided by the differential or the small a as previously. And then we can just once again integrate from this angle to this angle. So from the vertical, so phi initial is here and phi final is here. So the final, so to find the potential between A and B in this first case is equal to the integral of E dl, and using the differential Ohm's law, which relates the electric field to the current density vector, we have this, because the dot product, these are parallel, both dl and j. So then we just integrate this from phi I to phi final, and this will give you something. And the second case which we consider is plugging in current from everywhere, but taking it away at B. Well, clearly this is similar to what we just did, except that we just multiply every single current by -1, so we change its direction, and then we just rotate the sphere. But this clearly doesn't change the potential difference. So the potential difference in this case will also be V. And when we sum these two cases together, we get that there is a current I coming from A and current I leaving at B, which is what we wanted, but the total potential difference U is equal to 2 times V, so the effective resistance is 2V divided by I. Okay. Problem number 25. 10 to go. The idea here is that it's just classic. It is just so we have neutrons coming over a film with some thickness D, and there's some detector here with some width W, and there is a stream of neutrons coming through this at some speed V. The idea here is to realize that this is just diffraction, a situation of diffraction where we use the de Broglie waves, basically. The de Broglie, so basically just particle diffraction. So the de Broglie wavelength is h divided by mv, and this is one slit diffraction, in which case the intensity, which in the case of particles refers to the probability here, the probability distribution will be proportional to the I have to check. The sinc function. Yes. I think that's the name. Yeah. So the sinc function, I forgot its name. The sinc function of pi d in our case this distance here is r, x divided by r squared plus x squared divided by lambda and squared, so sinc squared. Sinc squared, and you just have to normalize this probability distribution. So p is some p naught sinc blah blah blah, and this is such that the total p over dx from minus infinity to infinity is 1, and then you just calculate whatever the final solution will be, whatever is the fraction from w over 2 to w over 2, and this is just a basic result from the one slit diffraction or interference. You will find this in many textbooks. This at least derived also in Jan Kalda's wave optics handout. So you will just integrate this, and this basically gives you the solution. Maybe you wanted to put percentages, so that's that. All right. So I don't find this particularly difficult. So 26. This was a bit more interesting. So we have a container with some gas at some temperature, initially at some temperature T0, but a constant pressure P1. And it is connected to a small hole to the outside world, which has pressure P2 and a temperature T2. And the idea is to find how long it takes until the temperature reaches a certain temperature. So I think it was to find the temperature to double in this case. Well, we just want to find the how does T depend on time. So how does the temperature depend on time? Well, first of all, we were given the rate of effusion. So the amount of particles inside the box will be 2an v kb T1. So T1, so T is just the temperature of the box divided by 2 pi m. This was basically the result which was given. You will get the same result when you use that P is equal to NK. PV is equal to nkt to phi, which is dn dt. Okay, and it's the point is that there's 3 particles coming in, but 1 leaving out. And the energy the energy increases due to these particles that are coming in, and the total energy of the reservoir for monoatomic gas is given by nkt, and the average energy of the particles entering through or going out is 2 kT of the respective temperatures. This was also given in the problem statement. So we can find out the rate of change of U, which is 3/2 nkt t, 3/2, and using this dn dt, it's 3/2 because once again there's 3 so this is the total rate, and it is 1 in 1 part due to the rate of going out, and the rate of going in is 3 times. So 3/2 dn dt, 2k 2kt minus 1/2 dn dt. Oh, this was t2, and 2kt1. And then basically we have solved this problem. We know what dn dt is with respect to t, and we will basically, when we perform this differentiation, then we will get that dt is a/v kt to pi m for t. But this was this is easy-ish given the information we gave, so that it's 2 kT and what's the rate of effusion, but those are very hard to derive by yourself. That's the point. And to give a better explanation of this 3/2 is that this is the total rate, but the rate of effusing is is 2 an/v blah blah blah. So to facilitate that into the energy that is coming in, we have to multiply it by 3 and divide by 2. And the rest here is, oh, and also this is using the notation of the model solution, using the notation I gave. It's this, and this can be solved exactly, but you can just integrate numerically. Anyways, and we continue. I am trying to put the pace up. Like, if the model solution is clear, I won't explain it too much, because these later problems are like clear for those who tackle them, basically. But if there's some, and also because I have been talking for 3 hours now, I want to get this over with, so I'm just trying to increase the pace a little. So if there's, I won't be explaining the most trivial stuff here anymore. So the air cushion. So we have a cylindrical air cushion, and then we add a plate on top of it. It will squeeze, and we want to find, I think, the final width, which I will call W. So we were also given that this originally had R, radius R. There's also some length to it, but we don't really care about that. but the length is L. And there's some surface tension gamma, and this has mass m, this slab which we add. And the gas inside is incompressible. You can think about how good of an approximation that is. But you can also think of it being filled with liquid. So, first of all, the idea, or the main idea to realize is that the gas inside will have some increased pressure with respect to the outside world, which comes from the Young-Laplace equation, because this is all, and it depends on the radius of curvature, and in this, whatever the radius of the curvature is, the main idea is that there is no radius of curvature at the end of these of the cylinder. So whatever the radius of curvature is, we have this cylindrical Young-Laplace equation. You can derive it from the general Young-Laplace equation, or you can use some other methods. There's plenty of resources for that online. And the idea now is the shape of this cushion will be always smooth, because the only force the only linear force, and by linear I mean force per unit length, for any part of this cushion comes from the surface tension. And thus, for any small part of this cushion, so let's look at this from the side. So if I pick this small line of cushion, the only notable forces that act on this part come from the surface tension. The gravity will be negligible, and everything else will be negligible. So when I look at the part in contact with the ground and the slab, whatever happens after this, it has to be smooth. And that leaves us with a semicircle, which connects this. And why it's a semicircle and not some other smooth shape like this is the fact that the surface tension provides a potential energy which is equal to the which is proportional to the area. So the shape of the free part will minimize the surface area, and that will happen with circles, as is well known. So the only smooth shape to minimize the area is these semicircles. And these will have some radius r. And using the Young-Laplace equation, this is the pressure inside after that. Okay. So now we just use some force balance. The force on the slab will from the cushion is the normal force, and that just counteracts the gravity. Yes. For the top part of the cushion, there is a force N acting from above, but then the air inside provides the force up. So that will give us N is equal to, and let's give this flat path some length A, and that gives us A times the length of the cylinder delta P. So that is the pressure, force from the pressure. And similarly, for the flat part, we get the same idea. But because these are connected with semicircles, we know already that both of these must be A. All right. So now we can solve that A is equal to mg divided by L delta P. And then the height here is simply 2r. And because we have incompressible gas, the volume must be conserved. But because the length is the same, it only means that this area must be conserved. So we get that pi r squared will be 2ar plus pi r squared. And now we can plug in mgl delta p, and delta p is gamma over r. We get pi plus mg gamma l r squared, and thus we find whatever r is, blah blah blah, and w is a plus 2r, which turns out to be mg gamma l plus 2r. Okay. Then SOPI oscillator. This was also a problem of mine. I think the solution once again is quite clear. I will, however, explain how I've calculated these things. And the main idea is that we want to find, based on what I did earlier, we want to find the kinetic energy and the potential energy with respect to some coordinate up to second order. And that will give us the small angle oscillation when we differentiate this. And in this case, it turns out to be because we have originally a square frame where we have some masses q at each hinge, and each bar has some mass m, and then there is some surface tension. It turns out that the ideal way to parameterize things, this is not respective of how it deforms, but it will be a rhombus, the shape always, because the lengths of these sides are conserved. And what we are, and I am working for many things, it is the easiest to work with this picture. So where both of these lengths have been differentiated by theta. So let's first calculate the potential energies, then I will calculate the kinetic energies, and then I will talk about common mistakes. This is a very bad picture. But the first idea is that the potential from the soap film is 2 times sigma times A. This is 2 times because there's 2 surfaces. There's above and below. Both of these surfaces will provide potential energy. And this can be easily, because I can split this rhombus into 2 triangles, and this triangle here, here is some angle phi. I can find that this is 2 sigma 2 sigma L squared sine the area of one of these triangles is equal to 1/2 L squared sine of phi, but phi is 90 degrees minus 2 theta. So sine of phi is equal to cosine of 2 theta. And because this is comprised of 2 similar triangles, thus the area, the total potential energy, is given as such. And this we can expand up to second order by 2 sigma L squared 1 minus 2 theta squared. Okay, fine. Then using a similar picture as above, so we have our rhombus looking something like this. It isn't that important, but we have some theta here, and we have this 45-degree line slicing through the rhombus. And I should write this a little bit more, or draw this a little bit more carefully. Let's do like this, and then let's do something like this. Okay, and then we have this 45-degree angle here, and it is well known that for rhombuses, the perpendiculars intersect perpendicularly. So this is 90-degree angle, and because this is theta, this phi here, this case, must be 45. Maybe I should use this phi here is let's not use phi. Alpha is 45 degrees minus theta. I can now find this blue length to be, let's say, blue length is equal to L. The blue length now clearly is 2 times L times sine of 45 degrees minus theta. And the green length, let's say, cursive L is 2L sine 45 degrees plus theta, because it's the cosine, and cosine 90 degrees. So you could alternatively say this is cosine 45 degrees minus theta, if you really want. And thus the electric potential energy is equal to kq, so k is the Coulomb constant, L 4. This 4 comes from, because all of these, all the charges which are next to each other have a constant length. So then this blue distance here, sine, I will use the notation in the solution now, plus 1 over 2 sine pi 4 plus theta, and you can expand this also to the second order. Theta squared, just barely. And now let's calculate the kinetic energy. The kinetic energy, I will not show the rigorous way to do it, but you can confirm that this is true if you really want. And but the fact is that the instantaneous center of rotation stays roughly still, so up to second order of theta and its derivatives, you can say that the center of rotation of each bar is stationary. So if we consider the initial case, then we have, for instance, that this bar here is moving toward the center, and this is moving away from the center. We can find the center of rotation from the perpendiculars of these. So at somewhere like this point here. So this rod is simply rotating around this this pivot point. And the kinetic energy then of this one rod, and there's 4 of them, So 4 times 1 over the moment of inertia theta squared. And the moment of inertia is the moment of inertia with respect to the center of mass plus mr squared, where r is this. And using some geometry, you can find that I is then this. And I should say 28 continues. Right? And this gives us that the kinetic energy is 2/3 ml squared theta dot squared. And then we are done. Then it's the same as previously. For example, what was the problem number? I think it was 7. Yes. So then you can use this formula, for instance, or just differentiate the total energy. I want to note out that there's a common faulty solution, or there's common mistakes. The first mistake, which many people did, was to not notice this factor of 2 here. So forgetting that there's 2 films. The second problem is that some people correctly, so if we orient this square like this originally, some people say that because initially the speeds here and here are equal, then that when it deforms, that the deformation here, x and y, are equal. Of course, these are wrong directions, like this. So if this moves a distance x, then this moves a distance y. That is not true. You have to use the Pythagorean theorem. And if you don't take the Pythagorean theorem, you won't get the correct second order terms for the potential energies. You have to take the Pythagorean theorem into account to be able to get the correct second order terms. So the Pythagorean theorem will add second order corrections which are relevant for this problem. Okay, 29. Relativistic scattering. I will already orient this the way okay, so I will orient this the way it is used in the actually I will have a short toilet break for now, so I'll come in like 1-2 minutes and I'll get some more water, then I will continue. So I'm back. Let's continue. So I will write this or draw this diagram such that the speed of the particle after, or was it before? So before scattering is already v. So that means that there is the initial photon is coming, or the plane wave is coming at an angle alpha in this direction, and it will scatter omega will be, I think, theta minus alpha here. Or maybe alpha minus theta, but I think it's theta minus alpha. Okay. So now we will just use basic four momentum considerations. That's always the easiest to do with photons, because that will immediately give you the correct Doppler shifts and whatever. So um, and the idea is that because this particle is moving, so what we want to find is what is the angular frequency of light scattered at this specific angle, basically. And the main point here is that if this particle was still, then it would just refract, it would scatter light into all directions uniformly. But because it's moving, it's not symmetric. So we have to first go to the symmetric frame to do stuff. So we first transform into the reference frame of the particle. And now we want to find the omega in this particle frame. Well, for momentum in the lab frame, clearly, again we will use C is equal to 1. The energy is simply omega. Actually, we will use the wave vector for vector, but that is basically the same as the for momentum. Because if you think about it, E is equal to HF is equal to 2 pi h omega, or was it omega over 2 pi? I always mix them up. So you just have to divide by 2 pi h, basically, to get to this vector. And then the momentum terms here are these. And in the and now we do a Lorentz transformation, and this first term will transform just like any other 4 vector. And a good example of a 4 vector is the t, x, y, z. So the the traditional 4 vector, the 4 position or whatever is its name. And how does the t component transform? The new t component is simply t. The original t is simply something like gamma t minus vx in c is equal to 1 coordinates. So what will be the first coordinate in the lab frame? Well, that's omega gamma 1 minus v cosine alpha. And because this gives the frequency, this wave vector 4 vector, wave 4 vector, I would say. So this is the frequency inside of this frame where the particle is still. Then it will scatter this omega 1 frequency at every direction uniformly. So let us consider an arbitrary phi direction where it starts to scatter around. Then the 4 vector in the lab frame would be simply omega 1, omega cosine phi, omega 1 sine phi. And then we transform this back to the lab frame using again the Lorentz transformations. So we get 1 gamma 1 plus v cosine phi omega 1 gamma cosine phi plus v omega 1 sine phi. And in the lab frame, the direction at it which it is going in the model solution is delta, so the tangent of that angle delta is equal to the y divided by x components. So we get this. But because we were interested in the direction of in the direction of theta minus alpha, delta you can just set to be theta minus alpha here, and then you just solve for everything based on the initial conditions. So we know what omega is originally, and this here is omega prime, and from this you can solve the delta, and when you know the tangent, we know what tangent delta is, thus we can solve for phi, and phi, when we know, we can find what is omega prime. So that's simple enough. Just checking something before I continue. Okay. And then we get to problem number 30. There's not much I want to say about this problem. This is very just bashy. So I won't really have, at least I don't have an elegant solution for this. But I will still present the solution quickly. So the idea is that we have a roller on flat ground where we have some mu, coefficient of friction mu. This has some mass m, and then there is a string which we are pulling at a constant tension, and we want to find when does theta have a local maximum for what is the minimal value of this for that to be. Well, there's two regimes. First, it will roll without slipping, and then it might roll with while slipping. And yeah, so let's consider the case where where we have rolling without slipping. So the total force is simply so the positive direction will be towards right is the tension minus the friction, and thus the acceleration will be t minus f divided by m. The total torque with respect to center of mass will be, and we are assuming that the friction is at the opposite direction. If our assumption is wrong, then everything will just change accordingly. T, and this has some radius r, tr cosine theta plus fr, right, and thus the angular acceleration is simply tr cosine theta plus f r divided by mr squared. And Because this is rolling without slipping, we have that A is equal to R alpha, and thus we can solve that the friction must be T1 minus cosine theta divided by 2, and this can only be smaller than mu mg, so the slipping will stop when theta reaches the arcus cosine of cosine of 2 mu mg divided by t, theta critical. And we also are interested in the angular speed at which this happens, because when we go to the slipping regime, then the angular frequency, the angular speed starts to slow, and we are reaching the angle, the maximal angle. The model solution provides a very elegant way to do this, and that is again using that alpha is theta dot dot, is to note that that theta dot dot, which we know to be T1 plus cosine theta 2mr, this can actually be written as theta dot d theta dot d theta, which makes this really easy to solve what is theta dot. So you just integrate this by you just basically solve this, integrate both sides with respect to d theta, and you get that t theta critical is equal to t theta critical plus sine theta critical divided by mr. And you can use the same trick for the rolling without slipping period, but now the friction is simply mu mg. And you will, if you use the same trick, but now this right hand side will be different. It will be t cosine theta mr plus mu gr. When you derive that, you will get that the theta maximum will be you will get theta m dot squared is equal to I'm running out of space. You will get some function, let's say, which depends on theta, but because theta m is the maximum, this theta dot must be 0, and then you just find out this function depends also on t mu mg. So you will, because I don't want to give another slide for this, you do the integration using the initial conditions, and you get this equation, and then you just find, for example, using some graphical calculator, for which value of this you can have the largest theta m. So again, we are done with the physics. Then we get to the interesting problems, I would say. So 31. Solenoid spring. In this case, we have a solenoid connected to a battery, but the solenoid has this small ring of mass m, which can oscillate slightly. And the inductance of this coil initially is L naught. This also has some spring constant K and has some rest length L naught. and no area given. And initially there is some I flowing through. And the key, and we are given that this resistance is really, really, really small. So we are talking about that this resistance is much smaller this resistance is much smaller than well we are given that it is really small. The right hand side would be dependent on L and the oscillation frequency basically. Wait a second, I got a message. No, not relevant. So okay, so the main idea here is to realize that once again it is useful to write this using the total energy. The total energy will be dependent on the magnetic energy, it will be dependent on the energy of the coil, the spring, and it will be dependent on the kinetic energy. But now the key insight is that because this resistance is small, within the duration of one oscillation, because the resistance is really small, within the duration of one oscillation, flux will remain constant. Why? Due to Faraday's law. Due to Faraday's law, the EMF is equal to the change in flux. But because this EMF is equal to Ri, but R is really small, this is approximately 0. So phi is a constant. So the flux throughout the solenoid is roughly constant. And because the flux is NAB, this also means that the that B is constant. So phi const implies B const. But now, just as before, the magnetic field energy is B squared divided by 2 mu AL, where L is the length of this spring, which is L naught plus X. But all of this is constant, and this potential energy is only up to first order. And because if it's only to the first order, it will not be relevant for the second order derivative. So basically, this UB term is completely negligible, and we can immediately see that omega is k over n. Right? Then 32. For this I will provide an alternative solution. So the idea is, or I will explain one of the footnote solutions better. So we have a string at its normal mode, just oscillating up and down, it's fundamental frequency, but then we start to make it shorter by a slight amount, by very slow. And the model solution basically finds the energy of the string oscillation and finds the force which the finger exerts on the string, and relates the change of the energy into the work done by the finger to find how A changes. I will do it a slightly different way. The first idea is to think what is the force, the vertical force on this string. Well, the vertical force of a small part on small part of the string. So let's take a small part here of length dx. The y force is, or maybe it should be dl, doesn't really matter, is equal to the mass of the part I am looking at times the acceleration, and the acceleration is simply the second derivative of with respect to time. But because this is a fundamental fundamental oscillation, the y is given as sine pi x divided by L sine omega t. So this will be minus omega squared L dl y. So the the restoring force will be proportional to y, so it's linear. And when you have a linear system, it abides by the superposition principle. So I can look at this string as a superposition of two other three-dimensional strings. So if we look at it from like the end, the it is oscillating like this, the string, and just like previously, I can write this oscillating string as a superposition of two rotating waves, basically, which are rotating in these directions. But now, if I look at one of these, so it's basically a jumping rope, not a, it's jumping rope in Finnish, as a skipping rope. But now if I look at one of these skipping ropes, so I have a skipping rope here, and it's rotating like this, and I exert a force, the finger exerts a force here to the string. This means that the angular momentum of this end, at this end, is constant. But now I can find the angular momentum using dimensional analysis. It depends on the mass of the string, it depends on the amplitude of the string, and it depends on the rotational velocity. And to make this proportionality to work dimensionally, so I can actually use, I should say, I use dimensional analysis. So we have some numerical prefactor, let's say k, then we have m, a, and omega. And to make this work, a must be squared. But now m is given to be just L times lambda, a squared omega. So L, which is constant, is proportional to LA squared omega. But now L is, I have two L's here. This is confusing. The angular momentum should be probably written as L, as a small l. But now the omega and L are related in the original string, which is composed of of a superposition of two waves going in opposite directions and reflecting off the ends, basically. This is well known. And these have some sort of speed, v. And they have some phase speed and they have some group speed. But because the waves don't disperse clearly in this situation, we see that both speeds are equal and constant and are equal to omega over k, which is again the wave vector. But this is proportional to omega L. But this v is constant, as I stated. So this means that omega L here is constant. But because the angular momentum is constant, that means that A must be constant. So A is constant. Okay. Then the chess problem. This is more like combinatorics slash probability. The idea is that we have a 4 times 4 grid. So 4 times 4 grid. Let's see if I'm able to draw a 4 by 4 grid. Challenge impossible. Like this. And we have some particles inside here originally at each point. And each of them will start moving at the same time. So after every second, each particle will randomly move as a knight does in chess. And then we have to find that when an equilibrium is reached and we provide this each cell a constant temperature T, what is the energy of each cell, and we want to specifically find the highest and lowest energy states and differentiate them. And again, the idea is to use the Boltzmann distribution. The probability of a particle being in any cell is proportional to E minus the energy of the cell times kT, where K is once again the Boltzmann constant. And so now we just have to find what P is. Because now if we know the highest and lowest probability, these represent the highest and lowest energy states, then we can just take the difference, P high and P low, to get the difference. So you will have actually I should probably P low has the highest energy like this, and this will be equal to E high minus E low divided by KT, which gives us that E high minus E low is equal to KT ln P high P low P high. So now we just have to find the probability, and this is combinatorics slash probability things. And I really like the solution provided in the model solution. So the first idea is that the probability of something to jump at cell X is we should probably say that the probability for something to be in cell X can be found from summing through all the possibility all the cells I, or maybe let's use U as in the solution, times the probability of a particle being in the cell U times it going from U to X. And P from U to X is simply 1 divided by the degree of U. So and the degree here is basically the number of other cells that can reach it. So to get from U to X, it's simply 1 over the degree U. Because if there is, let's say, because and the point is that all the cells that can reach it are also the cells that the particle from the cell U can reach. So let's say if for instance here in the middle cell you can reach 1, 2, 3 and 4 cells, then the probability of it landing here is simply 1 over 4. So that is quite trivial. And to make a guess of a solution that can fulfill px is equal to sum over u pu divided by degree of u. A self-similar solution could be that we just guess that px is degree of x summed by their all possible u's. This is like a reasonable guess to do, and you can then check that if this actually fulfills everything. And it turns out that it does, and you can check all the degrees of the cell. The highest degree is 4, the lowest degree is 2, and then you use these. And anyways, and after 33, everyone knows that the next problem is 35. Okay, good. Everyone agrees with me. There was no problem in between. Never was. A figment of your imagination. So now we get to the tired Flappy Bird problem, and this is definitely my favorite problem of the problem set. So the idea is that we have a Flappy Bird which can jump in air, but after each jump, its velocity will be smaller. So in this case, something like this. And we want to find the largest horizontal distance it can reach. So we can start again using the envelope curve. So for the first jump, there is some envelope through which includes all the points from which it can reach. And clearly, the second jump should be on this envelope curve, because otherwise, so let's say if I jumped here, it is clearly better that I would have jumped from here, at least, clearly better. So the envelope, and I can reach this point, so I should have jumped like that. So the next jump should be on the envelope curve. Well, what is this first envelope curve? So all the points which we can reach within one jump, and I will use the notation on the model solution, is HO1 minus AO1 x1 squared, where HO1 is H plus V1 squared 2G, and AO1 is G over 2V1 squared. So now we want to find, because this first envelope curve works so well, maybe we should find the envelope curve for two jumps. And because the second jump must happen on this envelope curve, so our starting position has to be somewhere x1, y1, and we want to see what are all the points x2, y2 which we can reach. So let's take a point on this envelope curve, and let's consider the envelope curve of the second jump, which I have drawn with yellow there, like the start of it. Well, the second envelope curve clearly is y2 is equal to y1 plus h21. So this is basically this HO1 here, minus a21 x squared minus x1 squared. So I just do a coordinate shift basically. And h21 is the height after the first, is the height of the is the height of the second, the highest point the second jump can reach, basically, from our jumping point. And that is again by the envelope curve, that is v2 squared divided by 2g, and a21 again from the envelope curve we have this. And now I can rewrite, and now we can, the same way we derived the envelope curve in problem, I think, the ping pong 1 problem, I derived it, it was a long time ago, 18. We can use the same strategy to find the envelope curve for the second jump. And that is that there exists point, so if there exists a point, point x2, y2, which I can reach, then there exists at least one x1 for which this equation is true. So if I can reach x2, y2, then then there exists some x1 for which I can there exists at least one x1 for which this equation is true. But on the other hand, this equation is is a quadratic equation with respect to x1. And I can also plug in y1 from here, so I should actually probably do that. Like that. And this is clearly a second order, a quadratic equation with respect to x1. So if there exists an x1, then for which this equation can be true, then the discriminant of this equation with respect to x1 must be non-negative. And if I write this in standard form, so expanding everything so that the discriminant is easy to calculate, mainly. H1 minus H21, and this is equal to 0. The discriminant must be non-negative, from which we find using math, just math, that all the points y2 and x2 are related by, which we can reach, are related by this inequality. So the envelope curve is clearly when these are equal. So the second envelope curve will be the one that fulfills this equality. And now I can use an inductive reasoning, or just noticing that using similar reasoning, we can find yn to be equal to sum of j1 to n hj, j minus 1 minus we say minus 1, we say minus a, j minus 1 minus 1. And looking at the previous expressions for h2 and a21, we can clearly see what they are. So we start with the sum over the h's. And of course the final envelope curve, when we allow for infinite jumps, is the limit. So y is equal to the limit of where n goes to infinity of y. And this will give us some series which we have to evaluate. So starting with the h series j minus 1, this is clearly equal to h plus sum J1 Vj 2g is equal to h plus v naught squared 2g sum of j is equal to 1 over infinity over j squared. And this is the famous slash infamous Basel series, for which you can all not this is a joke, but basically all self-respecting mathematicians and physicists should be able to recognize that this is equal to pi squared over 6. Yes. And that gives us pi squared over 12 v naught squared divided by g. Similarly, we can evaluate the A series to be equal to g 2v naught squared sum over g1 j minus 2 minus 1, and this is equal to 3 over pi squared g v naught squared. So the final envelope curve is h plus pi squared divided by 12 v naught squared g minus 3 pi squared g v naught squared x squared. And looking back at the original situation, we just have some parabola, and we just find so the entire envelope curve is some sort of parabola. So we just find at which point it intersects the ground. So you just solve this equation is equal to 0, and the solution x for that is equal to L. And you will be able to solve that L is equal to pi squared over 6, 1 plus 12 pi squared gh v naught squared 1/2 v naught squared divided by g. And yes, that was all of the problems which weren't retracted from the competition. If I had more time, i.e. if this wouldn't have gone for so long, I would have wanted to talk about problem 34 and self-duality, or duality in general, even though the grid itself wasn't dual due to a stupid mistake in the problem-making procedure, but I could have explained duality better, but I don't now have time for that. I want to go do something else. So anyways, here was all the online physics Olympiad problems, and I hope I was able to provide some insight to some of these problems, i.e. where the solutions come from, and especially with like what was it, problem number 7, to be able to show the analytic version without any shortcuts. So yeah. So just to answer the chat before I leave, yeah, the proper version of that problem should have asked what is the current from down to from top to down times the current from left to right, and that you can solve using duality, and that turns out to be the solution I had in mind. So that would be that 26 squared ampere squared. Should be. Unless I'm thinking it wrong. But anyways, this is everything, and I hope you enjoyed the problems. I hope you enjoyed the solution presentation. And with some teams we will see at the invitationals, and let's hope that the invitationals are interesting. I can admit that these problems this year were a bit easier than they used to be, So probably next year we have to up the difficulty a bit. But anyways, thank you for everyone who watched this, and thank you for everyone who will be watching this in the future. I will go start creating some problems for the invitationals. So, goodbye.